that are going to be less than the energy of the incident photon. There is no issue. How do I get anti-stokes? I get anti-stokes if I start from this level. I go up and then I come back here. So I start from an upper level. The molecule absorbs this energy, goes to the virtual state, but when the scattering happens, what is the molecule actually doing? It's actually jumping from that state to a lower state, and therefore the scattered radiation now must have an energy that is this plus of course this difference, and therefore this will be pi scattered energy wise greater than pi incident, and I call that as my anti-stokes. So you do a Raman experiment, you are likely to see one process in which the molecule jumps from here to here and gives me this energy spacing. And what experiment is that? The Stokes experiment. The same molecule might jump from here to here and give me the same energy spacing. I am actually getting the same data in two different experimental regions. One in the low frequency or the low energy anti-Stokes region, and one the high energy anti-Stokes region. Absolutely identical information. So there is really no reason why we're looking at both, unless of course there are some issues with it. But there is one big difference between the Stokes and the anti-Stokes, and what is that? The intensity. The anti-Stokes lines will forever be low intensity. In fact, they will be so low in intensity that you don't even want to see them very often. You always want to be looking at the Stokes radiation. Why is the anti-Stokes line of weak intensity? Because I am leaving the whole process. I am leaving the excited state going up and then coming down. The population of this state is general. The reason I am using the word in general is because if you have a 2J plus 1 degeneracy, you have a problem. Therefore, I am saying in general. This population has to be less than this population. If this population is less than this population, naturally, this whole process has got to have a lower probability than this process. And that's the reason why you always find Stokes lines of much greater intensity than your anti-Stokes lines. Unless, of course, like in the rotational spectroscopy, this guy had a greater population than this guy. In which case, of course, this line would have a greater intensity than your Stokes. But in general, when we vibrational Raman, you will find that the population in V equal to 1 will be far less than the population in V equal to 0. And therefore, if this was, let us say, V equal to 0, and this was V equal to 1, population here, and let's say this is 1000 wave numbers, work out your KT, it's going to be e power minus 5. Hardly any population out here. And therefore, you will find that the anti-Stokes lines would actually be very hard to see. It might show a little blips. Whereas the Stokes lines would be quite easily observable in all these experiments. That's the reason why you want to look at Stokes lines most of the time rather than the anti-Stokes lines. Okay. Can you tell me a situation where you want to look at the anti-Stokes line and not the Stokes lines? In spite of the fact that this has got such low intensity, and I just made a comment that you don't ever want to look at an anti-Stokes line because it's going to kill you. Can you give me a situation in which you'll be forced to look at anti-Stokes lines rather than looking at the much more intense Stokes lines?
Fluorescence?
Yeah, if there is fluorescence, I excite here, and then there is this big fluorescence that we see over here. And if you actually go looking for the Raman, where is the Raman line under this? Something like this. This guy is swamping the entire region. You can't see the Raman line. So what do? Very smartly go and look on this side. It will be even smaller, but I am looking at that line not under a background. Here is this big fluorescence background in which I have to look up this Raman. Impossible, because the fluorescence will be like orders of magnitude stronger than what you will see for Raman. Therefore, it's a dumb thing to do, looking for fluorescence, Raman under that fluorescence band. However, what you can do is to go to the anti-Stokes region, and we know, thankfully, that there is going to be no fluorescence emission in the anti-Stokes region. And therefore, the Raman line is going to be extremely weak, no doubt, but it is still not going to be sitting under a background. And therefore, if you could somehow jack up your sensitivity of your machine and get signal with enough signal to noise ratio, you might still be able to look up this. Or in other words, you have a better chance of seeing the anti-Stokes Raman rather than the Stokes Raman in this case. That's probably one of the few cases where you would want to look for the anti-Stokes lines and not look for the Stokes line, because there's a huge monster sitting in the Stokes region preventing you from looking at the Raman line. And that's the reason why you would want to do this. But of course, I also said the other day, you can beat the fluorescence by simply using a long wavelength light. You know, the molecule absorbed at 400 and let's say fluorescein, its emission maximum is where? 510. So you use 600 nanometers. It's not going to absorb. So use 600 nanometers, maybe 700 nanometers, and then do the experiment. Well, you will see Raman lines quite well because we don't have fluorescence emission where the molecule is not absorbing. Again, there is a compromise. And what's the compromise? Less scattering, because scattering depends on 1 over lambda power 4. We said that. And therefore, if I'm going to be looking at Raman scattering using a 700 nanometer light, I'm actually dropping my scattering efficiency as opposed to 400 nanometers. Yeah, but then I'm dropping the fluorescence completely. And therefore, it's still a very smart thing to do to actually go and look for fluorescence, I mean look for Raman using long wavelength excitation like 600, 700 nanometers, 800 nanometers, rather than using 300, 400, 500 nanometer light, where I know my molecule will be very happy to give me fluorescence when I don't want it to. I'm actually looking for Raman. I'm not interested in fluorescence. But the molecule fluoresces, your son will be forced to look for the anti-Stokes line, which is really a huge compromise because it's such a weak intensity that you have to deal with. So anytime you do Raman, you're going to get Stokes, you're going to get anti-Stokes. Stokes is much more intense, anti-Stokes is far less intense. Almost the same information is there in both, but you will see that in some cases, very few cases, you will want to look at the anti-Stokes lines all the same. Now let's see how we can use this information and start to develop the spectroscopy of some of these molecules when you do Raman spectroscopy. Let me draw the energy level diagram for rotational stuff, and let us look at rotational Raman first. That's 0, that's going to be 2b, that's going to be 6b, that's going to be 12. That's the energy level, right? It goes as 1 and 2, 2 and 3, 3 and 4, and so on. If I do an absorption experiment, what do I see? A transition between this and this, that will come at 2b. A transition between this and this, that will come at 4b. A transition between this and this, that comes at 6b. And that's how we got our 2b spacing, and from which we can calculate all our b values, hence r and 4. If you do Raman, what happens? This is J. The molecule starts from here, where should it end? It can end back on itself, because delta J equals 0 is allowed. What's the other possibility? It can end at 2. Because we need a delta J equals plus minus 0 or plus 0 or plus minus 2. So I can start from J0 and get back to J0. It's almost like Rayleigh scattering. It is Rayleigh scattering, not even almost like it's Rayleigh scattering. But if I start with 0 and end up at 2, then of course I am seeing a delta J equals 2 transition. And what branch is that? S branch. So I'm going to be seeing an S branch. So let's say I have 25,000 wave number light that I'm using for this experiment. So it starts from here, it goes on somewhere up there and comes back and lands out here. So if my Rayleigh scattering is sitting at 25,000 wave numbers, and if my frequency is going higher in this region, getting bigger than that in small wave number, large wave number. So what is this difference? Let's say this is 10 wave numbers. And this is going to be, how much is that? So B is 5, it's 30 wave numbers. So the whole thing is going to be 40 wave numbers difference here. So which means if I go up and come back on this line, I'm going to be seeing a Stokes shift that is going to sit at 25,000 minus 40, and therefore somewhere over here. And that's my 0 to 2 transition. And what line is that? Stokes line. Simply because the energy of the scattered radiation is less than the energy of my incident radiation. What's the other possibility? I start with 1, I can end up at 3, and that's going to be the next line. And therefore you will find I will start developing the entire S branch structure for this molecule. And this is my Stokes. What's the other possibility? I can start from 2, and then I can get down to 0. I'm still delta J equals plus 2. But what sort of transition is this? It's an anti-Stokes. Why is it anti-Stokes? My scattered radiation has a frequency, has an energy larger than my incident light. Therefore, if I start from here and I get back to this curve here, at the lower state, it must be an anti-Stokes radiation. And anti-Stokes radiation will come at higher frequencies, and therefore it's going to show up in this region, because I have put my scale in such a way that my wave number will increase this way, and therefore you will see all the spacing that you get here must be consistent with the spacing you get here. If this is 0 to 2 and this is 2 to 0, then this will be the same. If this is 0 to 2 and this is 1 to 3, then this will be 3 to 1, and therefore you get this. What branch is that? What is delta J in this case? Delta J in this case, 2 minus 0. The upper state is 2, the lower state is 0. Delta J is plus 2. What is the upper state in this case? 2. The upper state is still 2. The lower state is 0. And therefore, in this case, the delta J is still 0. I mean, it's still plus 2. So in both cases, my upper state is 2, my lower state is 0. Only that in one case the molecule went from 0 to 2. The initial state was 0 and the final state was 2. In the other case, the initial state was 2 and the final state was 0. But in both cases, the upper state was 2 and the lower state is 0. Just like what we saw earlier in rotational spectroscopy. Whether the molecule does emission or absorption in rotating microwave spectroscopy, it doesn't matter. It is still a delta J equals plus 1 transition, because the upper state is always going to be greater than the lower state as far as rotational spectroscopy is concerned. There is no way, no earthly way by which in this system of pure rotations, your upper state can have a lower quantum number than your lower state. That's impossible. The only way you can get that is when you do vibration spectroscopy. The vibrational manifold of the upper P equals 1 level, and compare that with the manifold of states for the lower level. You can have all these complications. The upper level can have a bigger J than the lower, upper level can have a lower J than the lower, and the state at the bottom. But if I'm doing pure rotations, the lower state always must have a J that is going to be smaller than the upper state. There's nothing I can do about it. This is a Stokes line in which branch? S branch. This is an anti-Stokes line in which branch? S branch. Please keep that in mind. It's very easy to get confused. It's very easy to misinterpret this whole thing, saying that, oh, this must be an S branch and that must be an O branch. It's not an O branch, because the upper state is still greater than the lower state. Delta J is still plus 2. The delta J is not minus 2. It is plus 2. So this is in pure rotation. In pure rotation spectroscopy, you will see a Stokes line, you will see an anti-Stokes line, both of which belong to the S branch. Of course, you will also have a Q branch, which will actually develop in this case. But we will, for the time being, just look at the S branch level. Let's go to the vibrational part and see what happens in that case. So if you're doing vibrational spectroscopy on molecules, and j equal to 0. And then I have j equal to 1, j equal to 2, j equal to 3, and so on. And this is going to be 2b, 6b, 12b. And then b equal to 1, j equal to 0, and that's 2b, and 6b. And let me assume to begin with that the b is the same in both cases. We will not bring in the complication, but we know what the complication does, so there's no big deal. So when we finally remove that constraint, the b has to be same in both cases. It's not something that you are new to. You already know how to handle that. So it's perfectly okay to bring in that assumption that the b values are identical in both states. We know what it really does. Now see what's going to happen. Let's look at Stokes first. If I do Stokes, what am I really doing? I start from b equal to 0, j equal to 0, and let's say I'm doing vibrational spectroscopy. Where will my Rayleigh scattering happen? Let's also build up. Let's say this is 25,000 Rayleigh numbers. And let's say the mu increases, mu bar increases in this direction. That's 25,000, that's my Rayleigh scattering. Extremely intense, so I have to filter it off to whatever I want to do. Now what's my Stokes line going to be for a transition from V0 to V1? Delta J is still 0 plus minus 2. Okay, so if I start from V0, J0 to V equal to 1, J equal to 0, where do you think that will come? That's going to come at an incident light, which is 25,000 wave numbers, minus the energy difference between the two vibrational states, which is not rotating at all. We saw earlier, when we did vibrational spectroscopy, you could never access this state starting from here. Why? We had a selection rule that said delta J has to be plus minus 1. So if you start from 0, you can't end up on 0. You have to end up on 1. I don't have a problem here. I can start from V equal to 0, J equal to 0, and end up on V equal to 1, J equal to 0. Okay. And what branch is that? Q branch, because delta J equal to 0. But where will it show up? It's going to show up at 25,000 wave numbers, which is my exciting frequency, minus this difference between the two levels. And let's assume that difference is 1,000 wave numbers or 2,000 wave numbers. So which means, and higher frequency or lower frequency? Has to be lower frequency because I am losing this amount of energy. And therefore the scattered radiation has to have an energy that is less than the incident radiation. And by how much? By this difference. And that difference I'm going to say is, let's say, 2,000 wave numbers. It just doesn't matter what the number is. But if it's less, it's got to come somewhere over here, and therefore I will see the Q branch, which is delta J equal to 0, coming right here.
So what's the selection rule for V in Raman Spectroscopy?
Pardon me?
Selection rule for V.
Oh, selection rule for V. Again, same harmonic approximation. If you have a harmonic approximation, then of course it's going to be delta V equals plus minus 1. If it's an harmonic, then everything goes. I have this. Now what's going to happen to, how does the S branch develop in this? I start from V equal to 0, J equal to 0. And where is the S branch going to come? Start from J0, V0 to J2, V1. And what is the frequency of that scattered radiation going to be relative to what I saw over here? It will be less or more? Less. Because that flow is coming all the way back to here. But if I take this molecule and leave it in this state, which is J equals 2, I am therefore making a transition from J0 to J equals 2, and therefore trying to see where the S branch is coming, you will see the scattered photon producing an S branch must necessarily have an energy that is less than what I am seeing for this. So if that was this much, this one was going this much. And what is the frequency difference going to be between this guy and this? scattered radiation that I am now going to see is going to be this much. And how much is that? 6B. So 6B away to lower energies, I am going to get a line that is actually a transition from B equal to 0 to B equal to 1 and J equal to 0 and J equals to 2. So what is the upper state quantum number in terms of J? 2. What is the lower state quantum number in terms of J? 0. What is delta J? Plus 2. And therefore what branch is that? S branch. And what frequency, what radiation am I talking about? I am talking about Stokes. I am still talking about Stokes. Now what will happen if I start from J equals 2 from here and land up in J equals 0? It is still Stokes, right? It is still Stokes because the frequency has to be less than what I am throwing in. It is still Stokes. But what branch am I getting now? O. So if you give us I believe O, it's fine, it's O. And that's going to be panning out over here. So you have the radius scattering over here, and on the short wavelength end, you see a strong Q branch, and on both sides of the Q branch, you will have the S and the O. So over here, you are seeing the Stokes completely being produced. You have the Stokes radiation, you have the S branch of the Stokes radiation, you have the O branch of the Stokes radiation, you have the Q branch of the Stokes radiation. All of them coming up in the field. Now what happens? If I start the molecule here, of course, let us assume there is some population. Don't trap me by saying there is no population because there is no experiment. Because there is no population over here, you are going to see nothing in that region. But let's assume for a moment that there is some population out here. Then what can happen? I go all the way up and starting from B equal to 1, J equal to 0, and where do I land up? All the way down into B equal to 0, J equal to 0. What is delta J? 0. But what's my frequency of the scattered radiation relative to the frequency of my incident radiation? Greater or less? Greater. Therefore, what is it? Anti-Stokes. And where is it going to come? On this side. The Q branch of the anti-Stokes is going to be here. And what else can happen? I can start from here, which is J0, and end up on 2. So which means my upper state is J0 and my lower state is 2, and therefore what branch is that? That's my O branch. Therefore I am going to now see an O branch in my anti-Stokes side. Supposing I started with molecule up here and then came all the way down to 0, then what is that going to be? That's going to be the S branch in my anti-Stokes. So what I have is a Rayleigh. I have the Stokes counterpart in which I have the S branch and the O branch of the Stokes radiation in addition to the Q branch. I go walk up all the way over here. I have the anti-Stokes region, and in the anti-Stokes region I am going to have the O branch and the S branch and the Q branch. So you can see that your spectrum is actually doubling up for you. At the end of the day, you can tell me what information I have is the same as what I have over here. So why would I want to see both? Well, you would never want to see both. But the fact is the system gives it to you. You take it or leave it. You see both. You have the anti-Stokes, S branch, O branch, and the Q branch. Go to the Stokes region, to the lower wavelength, to the lower energy region or longer wavelength region, and you have the O branch, you have the S branch, and you have the Q branch. Excepting that these spectra will look a lot more intense than these spectra. In fact, I have even drawn this. These were the cases. Here it might be nothing like this, because I don't have population in the excited. If it's a vibration spectrum, you probably have so little population, you're not even going to see the anti-Stokes lines. You're going to see mostly the Stokes lines. But if this molecule does have population in the upper state, then of course you do see the Stokes and the anti-Stokes. But almost always the Stokes intensity will beat the anti-Stokes intensity hollow. You will always be in a position to be able to see the Stokes lines far better than what you would see the anti-Stokes lines. What I really want you to do is the following. Assume, I think that's what one of the problem is trying to do for you. I could have said this, I tried to build up the story in as nice a way as I could possibly could, but the only way you're going to really internalize it is if you take a system, calculate all these energy levels for the lower state, calculate all the energy levels for the V equal to 1 state, assume 25,000 wave numbers or 30,000 wave numbers or whatever it is for the incident radiation, and calculate for yourself where each of these lines will show up, plot it for yourself, and then keep staring. That is when you would really internalize what goes on in the Raman spectrum.